Hey everyone, this is the second half of the lecture about tolerances, and now I'm sitting in the way of this, and I'm sorry if I blind you. I'm going to try not to. Here is where we left off. Let me find my slideshow. There we go. We talk about tolerances. So scientists and engineers, we understand that when you take measurements, there's going to be errors. When you're producing things, there's going to be errors. And so we say, we got to allow for a certain margin of error. It's got to be something that's realistic as far as our expectations are concerned, as far as their production equipment is concerned. And it's got to be taking into account the client's needs and what the product's meant to do. So if you improve the precision of your manufacturing methods, your technologies, and the devices you use, then you can increase or decrease the little error that you got. You can also standardize your procedures if you find that like making things a certain way, the steps that you take around that production process, if you need to make them more strict so that you can also guarantee a small error. But unfortunately, what that can do is that can really dramatically increase your costs. If I need to have very, very highly specialized, delicate precision equipment, it's going to cost more than if I'm just like chopping blocks up out of wood in my backyard. All right. So here's an example of a tolerance and how it's written. This is, I used to be a physics teacher as well, so I kind of have experience with these balances. Here's a balance. It looks like it's about 340 grams. I couldn't quite tell from, I couldn't quite read it. But I Googled how many ounces is in a can of soda, and I made up the grams number from that. So let's say if a physicist takes a measurement, they use a balance to measure the mass of an object, that's going to be in kilograms and grams, and they find the mass to be about 340.07 grams. And she's confident that her equipment's pretty precise. She knows she can figure out about 0.02 grams, about 0.02 of a gram. I don't think these balances are that precise, but hey, that's I made up a problem and it might not be realistic. So she's reasonably sure about this equipment being only off by about 0.02 of a gram. And so that means she's confident that when she takes that measurement and she reads it as 340.07, she knows that it's no more than 0.02 grams more or less than 340.07. So it's going to be between 340.05 and 340.09. And that's what this guy here means. Oops. Here's a picture I took from Aurora Flight Sciences. They're down by GTR, the airport, and I've taken 2 field trips there, maybe 3, I can't remember now, and I wish I could take y'all, and I'm hoping to get a virtual one this year because they do some really neat stuff. They're doing aerospace, they're doing unmanned. The thing in the picture, I believe, it begins with an O. Olympia? I forget what it is. Lord, I'm going to have to look that up. This thing here is a solar-powered unmanned aerial vehicle, and it's big like an airplane is big, so it's like wide, but it's really skinny, really light, and it's got solar panels. When I was there in person, they showed us a clean room that they had where they have a pressure differential between the inside of the clean room and the outside. And what that means is they can constantly pump in or pump out the air that's contaminated and pump in fresh air that has fewer contaminants. So like in the air you breathe normally, you're going to get a lot of dust particles. You're going to get like fuzz floating around, maybe germs, maybe coronavirus. So, and this also applies like in hospital settings when you have quarantining people, you need to make sure that you don't have a lot of just stuff in the air that you don't want in the air, because if you open that door and all that stuff comes out into the general population. Anyways, it's neither here nor there. I kind of made up these numbers as well. Let's say the design of your clean room ensures that the level of airborne contaminants remains between 0.05 and 0.01 ppm. That stands for parts per million. So per 1 million molecules of air, there's 1/10 of a molecule at most of a contaminant. So that's pretty good, right? That's really good, actually. Let's keep away contaminants because we need to make these parts. They need to do what they're supposed to do. Otherwise, it's not going to be able to fly unmanned. It's not going to be able to get the power it needs to. It's not going to be able to do what it needs to do. So for someone like Aurora, they've got government grants. They've got contracts. They have money. If I'm building a drone in my backyard, I'm not going to have a clean room. I'm just going to, have to deal with contaminants and maybe put a mask on so I don't breathe on the circuit board, and ground myself so I don't zap this, I'm not going to have the technology of a clean room. That's for somebody who's got a company that's got a lot of money to spend on that, and their products reflect that. They do good work. They get good products. So when you're designing and when you're manufacturing and producing things, there's got to be clear communication between those two parties. If you need to tell them, like, what dimensions is it really important to have very tight tolerances, so that's got to be produced with increased precision and cost. And what dimensions is it okay if it's a little bit looser? It's okay if it's not quite the same. It's okay if it's a bit farther away from that value that I've written down. So often you got your precision and your costs are at odds, and so you got to make these choices, like, If I'm selling this product for only this much amount of money, if I'm selling wooden blocks for children, I don't need to make sure they're all exactly the same size. The kids are going to bang them up anyways. They're not going to be the same size. They cost $20 for a bucket of them. I'm not going to go spend all this time and energy making sure that they are within 1,000th of an inch in all directions, So sometimes it can be a really difficult choice, but that was an easy choice I just mentioned. So let's talk about formats. Types of tolerances. You have unilateral tolerance, one-sided tolerance. In other words, I have a hard limit here and it can go a little bit more in one direction or the other. It allows for variation just in one direction. You use a plus sign for one of your variations and a minus for the other. Theoretically, you could have it vary at two different amounts up and down, but right now we're just talking unilateral. This picture right here, let me gesture with the mouse, I've got a 1/2 inch hole diameter, and I can go up to 0.004, 4/1000th of an inch more than that, but I can't go any smaller. It's got to be at least exactly 0.500, and those zeros are important. That means it's not 0.51 or 0.507 or anything like that. It's 0.500, and after that, it can have different numbers in the decimals. 0.500 is the smallest diameter I can have that hole. It can go up to 0.504, that's fine, but it's got to be the right size. Usually that's because you're going to put a fastener in. Maybe you're putting a pin in there, and if it's any smaller than that, the pin won't fit. If it's any larger than that, the pin won't touch enough of the side around the outside to make a connection so that it doesn't come apart. So that's why we have tolerances. Things got to fit together. Things got to work together. Got to be smooth. Got to go together. Bilateral. Bi means two, lateral means sided. It's two-way tolerance. And in this case, it's even. It's the same amount up and the same amount down. So it allows for equal variation in both directions. You've got this fancy symbol here. Oh, if I click on it, it's going to go next. This symbol here is a plus with a minus sign underneath it. So it's like a plus with an underline. You can find that if you are in a Microsoft product, usually in equation editors where I go. That's an actual equation. If you look at this, if I click on it, it's an equation. Here's my equation tools. You can probably also find this symbol if you need to make it like that. But if you're handwriting it, it's fine. It's easy. Go back to the slideshow. So what that means is that if I have, you can't really see this the way they've done it. There's a decimal point. It's 0.250. It's a 1/4 inch diameter. But it can go up a little bit. It can go about 0.03 inches above or about 0.03 inches below that. It can be slightly larger, slightly smaller. So 0.253 to 0.247. Those are the hard limits they've got. You're looking for 0.250. That'd be excellent. But if you're a little bit above or a little bit below, as long as you're within that range, it'll be fine. Here's a dimension of a location of the hole. Notice that it's 0.05. That's a much larger number. So there's a larger amount of variance that's acceptable for the location of that hole. It's 1.5 inches plus or minus 0.05 of an inch. So 1.55 to 1.45. That's the upper and lower. I wrote sig figs matter here, and I mentioned it before, but it's how confident you are in the precision of your measurement. So that last line doesn't need to be on there. And the last thing we're talking about limit dimensions. So that's when you actually tell people what the upper and lower limit are. You don't say, here's a middle point, and it goes up and down. You say, here's the top, here's the bottom. In this case, you've got an upper limit at 0.505 and a lower limit at 0.495. Could conceivably you've written diameter is 0.500 plus or minus 0.005. Yes, depending on certain factors, I'm not going to get into it, but that's just another way of writing essentially the same thing for our purposes. It means that I cannot have a hole that's diameter is more than 0.505 inches. I cannot have a diameter that's less than 0.495 inches. So the other thing we want to talk about is the amount of tolerance. If you look at this, remember how it was 0.03 or 0.003, 3 thousandths. If I go up 3 thousandths and down 3 thousandths, that's 6 thousandths of an inch total. This one here is 0.05. If I go up 0.05 and down 0.05, that's a total of 0.1, 1/10 of an inch. That's a lot larger tolerance. And I was calculating those by just finding the upper lower limit and subtracting them. Here's that example right here. What they've done is they've shown you that if you take your tolerance, you take your upper limit minus lower limit to get your tolerance. So if I have this plus 0.05, if I add 0.05 to 1.50, I get 1.55. That's my upper limit. If I have, if I subtract 0.05 from 1.50, I get 1.45. That's my lower limit. This is the specified, this is the ideal. These are my limits. So the total is between 1.55 and 1.45. I subtract those, I get 0.1. When it's written like this, sometimes you just say, let's double 0.05, same thing. If you have a unilateral tolerance, then If I go 0.004 and the other one's 0, well, the difference between is going to be 0.004. That's just the way it works. You can always make your upper and lower and subtract them, and just that's a good plan. That'll work for you every time. So you may also put general tolerance notes. You might say somewhere, it might not be at that single hole, it might just say, hey, in this document, all decimal dimensions are going to be held to either to plus or minus 0.002, 2/1000 of an inch, unless specified otherwise specified. And here's a version of it like in a table where you'd see it like in a title block. They say all angle dimensions, they have a plus or minus half a degree. Linear dimensions, they have different number of digits past the decimal point. With 1 digit past the decimal point, that's to the 10th of an inch. That's not as precise as something that's got 2, which is to the 100th of an inch, or 3, which is the 1000th of an inch. So you'll notice that these tolerances also get smaller as the detail gets more precise. So best practice is to put some sort of tolerance on every dimension you've got, every single one, so that the company knows how to make it for you. You can either put just a general one out there, or you can go painstakingly every single one of them and put it in there. But if you have a lot that are the same, you might as well put a general note and then go from there. So for today, what we're going to do is we are going to make a table of the tolerances we've got. I don't have it on this computer. It's on that computer. I edited the last slide so I could show you an example. You're going to need a column, like a skinny column for the letter, a skinny-ish column for the type of the format of the tolerance, so bilateral, unilateral, limit dimension. A wide column where you can have like a meaning, what's that mean in words, and then a skinny column at the end for your calculated value of tolerance. And I'll show you that in a second. But what you're going to do is there's these two pictures. They're in the PDF. They're in the PDF, which is this right here, the PowerPoint. This is the PDF of it. I also have, these are slightly larger versions of both the conduit bracket and the axle stabilizer, which are, here's the conduit bracket, here's the axle stabilizer. The only problem is it doesn't have the A, B, C, D, E labels. So if you go and look at these guys, just reference back in the PDF here to find out A, B, C, D, E, F, G, H. Okay, so you know which one's which, and so I know which one you're trying to do. Here's the example I made. I said, here's a letter column, here's a format column, a meaning column, a calculated tolerance column. I did a handwritten version of it. Let me see at the OBS. Yeah, you can probably see it. My handwriting is kind of awful, and it takes up a lot of space. I figured it would take the whole back side of this page, or if it's a notebook, it's going to take the whole notebook page. If you want to go ahead and type it up, that is okay too. If you want to put it in like a Word document, this is the table I made when I made this the PowerPoint. But to make a table in Word, this is going to be a bit of a longer video because I just thought about this. To make a table in Word or Docs, which is going to be what's on your where's Word? It's what's on your Chromebooks. If I go here, blank document, let's insert a table. It's going to be 1, 2, 3, 4. I need a like labels line, and I got A, B, C, D, E, F, G, H, that's 8. 8, so I've got 9. I'm going to have to add 1, 4 by 8. Insert, there's an insert. Insert a row, doesn't matter where. Design, layout, design, okay. So yeah, I'm going to have the letter. I'm going to have the, what did I say? Format of the tolerance, the meaning of that, and the calculated tolerance. And so then you can always go grab these guys, move over. I don't need a lot of space for format because at most it's going to be like unilateral, bilateral. I don't need a lot of space for calculated tolerance. It's going to be a number. And so yeah, so here I'd say look A, I type my format in, I can type my meaning in. If it goes longer, then it will automatically make it a larger table field. So you don't have to worry about, like, some people like to draw the lines on a table and have it already gridded out. And then let's say you do that and you end up writing 3 lines here and you run over your line, it's going to be a mess. So I like to type it because my handwriting is so horrible and I don't plan ahead as well as I could when I make tables and write things by hand. So that's something to think about. But yeah, I said letter A is, I looked at letter A. Letter A is right here. And if I can zoom in and show you what letter A looks like. Oh, undo. Zoom. All right. Where's letter A gone? Now I've zoomed way too far. There it is, A. All right. It's kind of hard to see. The PDF hopefully is clearer. but it says the diameter is 0.138 plus or minus 0.01. That plus or minus, the only time you see that is when you have a bilateral, a two-directional thing. So if I were to go and fill that in, I'd say bilateral tolerance. What that means, the diameter should be 1.138 inches, but it can be 1/1000th of an inch larger or 1/1000 of an inch smaller. The calculated tolerance, if I were to add, I would get 1.139. If I were to subtract, I get 1.137. Subtract those from each other, you get 0.002. The other way that I like to think of it is I just say, look, it's 1/1000th in both directions, double it, 2/1000ths. There you have it. So that's what you're going to do. You're going to go through these. Find the bilateral ones are easy to pick because they're going to have the, undo again, undo. They're going to have the plus minus. Unilateral is just going to have plus something, and the minus is going to be separate. It's going to be 0, or the plus is 0, and the minus is something else. The limit one will have two different values. They won't have a value plus, and they won't have any pluses or minuses. It'll just be one top value, one bottom value, a upper and lower limit. All right. So that is what you're doing. Hopefully that's everything. I need to let these kids in. They're banging down the door 3 minutes early still. So y'all have a wonderful rest of the day. This is a very long video. I apologize. I'll talk to you soon. Bye.